Hey friends, welcome to the YouTube channel All About Electronics. So in the previous video, we have seen that how to implement the different logic gates using the NAND gate. So in this video, let us see how to implement these logic gates using the NOR gate. And first, let us start with the NOT gate. So let us see how to use the NOR gate as an inverter. So we know that if A and B are the input to this NOR gate, then its output is equal to A plus B whole bar. Now if both inputs are same, then its output will be equal to A plus A whole bar. And we know that this A plus A is equal to A. That means A plus A whole bar is equal to A bar. That means whenever both inputs of the NOR gate are same, then its output is the complement of the input signal. That means by connecting all the inputs of the NOR gate to a one input, it can be used as an inverter. Similarly, let us see how to implement the OR gate using the NOR gate. So we know that if A and B are the input to this OR gate, then its output is equal to A plus B. And for the same inputs A and B, the output of the NOR gate is equal to A plus B whole bar. So if we just complement the output of this NOR gate, then we will get the output of the OR gate. That means by passing the output of the NOR gate through an inverter, it can be used as a OR gate. Now we also know that how to implement this NOT gate using the NOR gate. So let us replace this NOT gate with the equivalent NOR implementation. So this is the equivalent OR gate using the NOR gate. Similarly, let us see how to implement the AND gate using the NOR gate. So if A and B are the input to this AND gate, then its output is equal to A dot B. On the other end, the output of the NOR gate is equal to A plus B whole bar. And using the De Morgan's law, equivalently it can be written as A bar dot B bar, right? So instead of A and B, if we apply the A bar and B bar as an input to this NOR gate, then its output would be equal to A dot B, right? Because in this case, we will get this A bar plus B bar whole bar, which is equivalent to the A dot B. Now this A bar and B bar signal can be generated by passing the input A and B through the NOT gate. And we already know that how to implement this NOT gate using the NOR gate. So let us replace this NOT gate with the equivalent NOR implementation. So in this way, we can implement the AND gate using the NOR gates. Similarly, let us see how to implement the NAND gate using the NOR gate. So if A and B are the input to this NAND gate, then its output is equal to A dot B whole bar, which is the complement of the AND gate output. Now we already know that how to implement the AND gate using the NOR gates. So here we just need to add the NOT gate after this output. And we already know that how to use the NOR gate as an inverter. So this is the equivalent NAND gate using the NOR gates. Similarly, let us see how to implement the XNOR gate using the NOR gate. But before that, let us understand this one thing. Now we have seen that if we want to perform the AND operation of A and B or A dot B, then we require total 3 NOR gates. Similarly, if we want to perform this A dot B plus C, then also we require 3 NOR gates. So here, with the first 2 NOR gates, we will get this A bar signal and this B plus C whole bar. And the output of the third NOR gate is the complement of this A bar plus this B plus C whole bar, which is equivalent to the A dot B plus C. So similarly, the Boolean expression A plus B dot C plus D also requires 3 NOR gates. So as you can see, all these 3 Boolean expressions requires the 3 NOR gates. And in fact, all the 3 expressions are similar to the form A plus B dot C plus D, because here this A dot B can also be written as A plus A dot B plus B. Similarly, this A dot B plus C can also be written as A plus A dot B plus C. So in short, any Boolean expression which can be written in the form of A plus B dot C plus D can be represented using the 3 NOR gates. So just keep this point in mind because we will use this concept while implementing the XNOR gate using the NOR gate. Alright, so now let us see how to implement this XNOR gate using the minimum number of 2 input NOR gates. So we know that if A and B are the input to this XNOR gate, then its output is equal to A dot B plus A bar dot B bar. Let's say this P is equal to A bar dot B bar, or equivalently it can also be written as A plus B whole bar. So now we can write the output of this XNOR gate as this P plus AB, where this P is equal to A bar dot B bar. Now using the distributive law, we can write this P plus AB as P plus A dot P plus B, right? And if you notice this expression, then it is similar to the form A plus B dot C plus D. That means this Boolean expression can be implemented using the 3 NOR gates, where this P is equal to A bar dot B bar. So as you can see, in this way, we can implement this P plus A dot P plus B, where this P is equal to A bar dot B bar. Now this A bar dot B bar can be implemented using the 1 NOR gate. So now the output of this NOR gate will be one of the input to this gate number 2 and 3. So the same circuit can also be drawn like this. And further, if I just rearrange this circuit, then it can also be drawn like this. So as you can see, using the 4 NOR gates, we can implement this XNOR gate. Or in other words, to implement this XNOR gate, we require minimum 4 NOR gates. Alright, so similarly, now let us see how to implement this XOR gate using the NOR gates. So if A and B are the input to this XOR gate, then its output is equal to A XOR B, which is equal to A bar dot B plus A dot B bar. On the other hand, this A XNOR B is equal to AB plus A bar dot B bar. So if we take the complement of this A XNOR B, then we will get this A XOR B. Or in other words, if we take the complement of this AB plus A bar dot B bar, then we will get this A dot B bar plus A bar dot B. So we already know that how to implement the XNOR gate using the NOR gates. So here, to implement the XOR gate, we just need to add the NOR gate after this output. And we already know that how to use the NOR gate as an inverter. So this is the equivalent XOR gate using the NOR gates. And as you can see, it requires total 5 NOR gates. Now there is another way by which we can implement this XOR gate using the 5 NOR gates. So let us also see that. So as we have just seen, this A bar dot B plus A dot B bar is the complement of this AB plus A bar dot B bar, right? So let us say this P is equal to A bar dot B bar. And using the De Morgan's law, it can also be written as A plus B whole bar. Similarly, let's say this Q is equal to AB. Now we know that this A plus B whole bar can be implemented using the 1 NOR gate. And we know that this A dot B can be implemented using the 3 NOR gates. That means this AB is equal to Q and this A bar dot B bar is equal to P. That means this XOR operation of this A and B is equal to P plus Q whole bar. So to implement this P plus Q whole bar, we also require one more NOR gate. That means in total, we require total 5 NOR gates. And this is the overall circuit. So here, this P is equal to A bar dot B bar, while this Q is equal to A dot B. And this P plus Q whole bar is implemented using this final NOR gate. So as you can see, this circuit also requires 5 NOR gate. So in this way, we can implement the XOR gate using the 5 NOR gates. So I hope in this video, you understood how to implement the different logic gates using the NOR gate. So if you have any question or suggestion, then do let me know here in the comment section below. If you like this video, hit the like button and subscribe to the channel for more such videos.